Um, a very good evening to everyone that has joined, and I hope that all of you have been having a great day. So, today is our first event out of the series of lectures that we are going to conduct as part of Zenith 22. And it's based on a very interesting and fundamental topic and will be delivered by Dr. Knoll. Dr. Knoll is a senior lecturer at the Imperial College London and is an internationally established scientist. He got his PhD from Stanford in 2010 and has done extensive work in the field of spacecraft engineering, specifically plasma propulsion. So, without further ado, let's give it up for Dr. Aaron Knoll, who will be teaching us about spacecraft propulsion. And welcome, Doctor. The stage is yours.
Okay, yes, thank you very much for the kind introduction. I'll introduce my research group and my research activity in the slide. So I'll go ahead and screen share now. So just let me know when everybody could see the screen.
Yeah, we can see it.
Yes, it's visible.
Yeah, the screen is visible.
Okay. Good. So yes, I thought I would deliver today's presentation on the topic of the challenges and opportunities that spacecraft propulsion presents as the world around us is changing. So of course, spacecraft propulsion itself has been around for a long period of time, but you can see now in the world there's new and emerging challenges, which makes the research very exciting. So a little bit about the background of Imperial College and the background of my own research activity. So Imperial College, it's been around for many years, and they have a long history, a heritage in space engineering. So 57 years, in fact, dating back to the launch of the Ariel 1 satellite in 1962. More background. So it's actually the 100-year anniversary of the Department of Aeronautics, which is the department in which I work, which is quite impressive if you consider how old aircraft are and when the first aircraft flew. So Imperial College was several years behind the first aircraft flight. They established a Department of Aeronautics, which at the time was very, very progressive. So much less significant, but it's now been 4 years since I formed something called the Imperial Plasma Propulsion Lab, which is my research group. So as well as having a good background in space engineering and a good background in aeronautics, Imperial College is also very well known for plasma science. So they deal a lot with high energy fusion plasmas. So these are plasmas that are intended to produce power. And so they have research in devices called Z-pinch, magpies, tokamaks, laser inertial confinement. So these are very high energy plasmas. And they also have expertise in very fundamental plasma topics. So things like laser plasma interactions, particle acceleration, dusty plasmas, space plasmas. So all of the topics to do with space engineering and space science are kind of unified within Imperial in something called Space Lab, which was launched in 2013. And it was a way to take all of these different activities which were occurring within college and combine them in one sort of network. So this brings together about 80 academics, myself included, from across Imperial, with joint interest in space-related technologies, doing science from space, using space-derived data products, the societal impacts and risks of space, and the applications of space-developed expertise, perhaps to other areas of society. And so having this network within Imperial allows us to engage with internal collaborations, engage externally with industry, do public events, and is useful with outreaching. The current director of the Space Lab, if you're curious, is an academic called Jonathan Eastwood, who's in the Department of Physics. So just to explain then how my research group fits within the context of Space Lab. So you can see over to the left-hand side, that's the Plasma Propulsion Lab, which I lead, which is then fitting into the Department of Aeronautics, which feeds into the space technology part of this overall Imperial involvement of space. both from the very upstream to the very downstream parts of space engineering. So this is a snapshot of my own research group. So I have three what we call PDRAs. So these are postdoctoral research assistants and four PhD students. Actually, as of January, I just have another PhD student. So there's another person on this list. So we have some nice test facilities within my lab. So most of the research that we do has to be conducted in a vacuum environment, so mirroring the environment of space. So to do that, we have vacuum chambers, and you can see they're quite large, so 1.5 meter diameter by 2 meter length. So you could quite easily get inside this chamber to set up your equipment. And then you pump down the chamber. So it goes to ultra high vacuum using a combination of cryo panels and turbo pumps. And this allows it to create a vacuum environment, which is equivalent to being in space in Earth orbit. And then we can test our propulsion technologies within the vacuum chamber using instruments like thrust balances to measure thrust, plasma probes to measure plasma properties, various sensors to measure the constituent products which come out of the thruster. In combination to like the experimental facilities inside the physical lab, we also have computational facilities that we're developing. So the type of modeling that we do within the group is plasma kinetic modeling, also known as particle and cell simulations. And we have a couple of codes that we're working on actively. The more mature codes are called plasma sims. So we have plasma sim 0D, 1D, and 2D, referring to the fact of the dimensionality of the simulation. So plasma sim 1D, for instance, is a high fidelity one-dimensional particle and cell model of a Hall thruster. 2D, as the name implies, it's a two-dimensional simulation of the Hall thruster. And 0D, this might be a little bit harder to visualize, but it's a so-called global model. So there's no spatial coordinate to the simulation. It's simulating the properties of the Hall effect thruster overall. Oh, and by the way, I'll get in a couple slides time, I'll explain what is a Hall effect thruster. So I'll come back to that topic. In development, we're working on a fully three-dimensional plasma kinetic simulation, so plasma sim 3D, and also something called plasma sim ML, where the ML stands for machine learning. So we're looking into the applications of machine learning in order to simulate and enhance the capability of the more conventional plasma kinetic simulation. Okay, so I like to start maybe a little bit with the big picture before moving into the details of the work. So first, when it comes to space engineering, you might ask, well, what's the point of developing new spacecraft? Perhaps devil's advocate, you could say, don't we have enough spacecraft already orbiting in space, and aren't they fulfilling all the purposes that we might envision? So what's the point? Space provides a unique resource to us as humans that allows us to accomplish things that we couldn't otherwise do without space. And we can divide this roughly into the following categories. First, space has the uniqueness of giving us a global perspective, meaning that unlike being on the surface of Earth, if you're in space, you can access simultaneously any point on the surface of the Earth. So this is especially, let's say, useful when you're doing communications, navigation, weather, and surveillance, because space provides the capacity to actually get every single land area of the Earth simultaneously. So for example, GPS allows us to know where we are. Weather satellites allows us to know what is the weather at any point on the globe, things like that. The second feature of space, which is unique, is that it's above the atmosphere. So if you're trying to observe from Earth into the rest of the universe, then we have quite a dense layer of atmosphere over our heads. And even though we perceive the atmosphere as being transparent, actually it obscures our view of the universe. And so if we position instruments above the Earth's atmosphere, we have a much clearer picture of what is existing in space. so we can make observations of other galaxies, other stars, much more clearly than if we're trying to observe them from the ground. Another unique feature of space is that it provides a gravity-free environment, what we refer to as microgravity conditions. And so this allows a unique chemistry, unique materials application, unique materials processing that can't be performed under the influence of gravity. And we're just starting to sort of scrape the surface of what we can do with material research and science in these microgravity conditions. Something I find particularly interesting, and I think maybe relevant nowadays, is the fact that space presents abundant resources. So we all live on one planet, essentially, and we understand more and more that the resources of our planet are constrained. And so the more that humans develop, the more humans that there are, the more resources we consume, we can see more and more the impact that we're having on our planet's biosphere. Space is different because space has a virtually unlimited amount of resources. So as humans continue to progress and continue to expand, I think it'll become ever more clear that we have to start using resources above those contained on our own planet. So people are looking into issues such as asteroid mining, collecting and harvesting solar power from space, looking at sources of water, and ultimately colonization, where it allows our species to continue to grow exponentially, but to not do so within the planet Earth, to do so on other planetary bodies. Finally, humans have a long, let's say, heritage of doing things just for the sake of doing things, right? So if there's new and unexplored things, then you can imagine that space exploration is serving its own purpose. So we explore it because we can explore it. And so I illustrate here a few arguably pointless things that humans have done, like putting flags into planets, putting cars into space, and sitting on piles of rocks. But the reason and the significance of what they're doing is the fact that they show that they can do that as a species. So I think this is maybe an unspoken part of the purpose of space exploration. Okay, so my research deals mostly with spacecraft propulsion, so I wanted to just start with a few basic concepts, so some fundamental theory. So if you're talking about plasma propulsion, or if you're talking about conventional chemical rockets, the underlying physics is all the same. What you're doing is you're expelling mass at high velocity out of your spacecraft, and that produces a force because you're losing the momentum. And the force is an equal and opposite reaction on the satellite itself. So in a sense, the mathematics is quite easy to understand. You have a force that you're generating on your satellite, which is a combination of two things. There's a pressure force, so this is the pressure at the exit plane of the rocket, and there's a momentum force. So this is equivalent to how fast and how much you're throwing out of the back of your satellite. So in engineering, we define something called a C term, which is a combination of these two forces, the momentum force and the pressure force, amalgamated into a single term. And that simplifies the mathematics, because then we can say that the force is proportional to the mass flow rate. So this is the change in mass of time of what we're expelling, times by this constant C, which accounts for both the pressure and the momentum force. And then you can express this in something we call a specific impulse. So this I subscript SP stands for specific impulse, and it's normalized by a gravity constant G, which is always referenced to gravity at Earth sea level, so standard Earth gravity, times by the mass flow rate of what we're sending out of our system. So a very simple equation. You can integrate this equation, so this equation here, to give you to derive what is the change in velocity of your object versus the amount of mass that you remove from your system. So this gives the very well-known Tsiolkovsky rocket equation, which says that we have our gravity term G, always 9.81, the specific impulse, so this is a measure of how fast the propellant is leaving the system, times by the natural log of the initial mass over the final mass of our system. So this is the only way that we know of to reliably change the velocity of our vehicle using rocket propulsion. Now, there's something important to comment here. The fact that if you want a large change in velocity of your vehicle on the left-hand side of this equation, you have some flexibility in how you can accomplish this. One way is to expel a lot of mass, right? So you can say, okay, if the final mass of my object is much, much lower than the initial mass of my object, then I can get a large change in velocity. But that necessarily implies that you're spending a lot of fuel because the only change in mass of your object is the amount of fuel you're consuming. So if you want to then say, no, I want a large change in velocity, but I don't want to expend a lot of mass getting that velocity, it means that your specific impulse needs to be as high as possible to give you this change in velocity. So that implies that you need to send mass out of your rocket as fast as you possibly can, right? So in this case, the higher the mass, the higher the exhaust velocity, the more capability you have in order to change the velocity of your spacecraft. So spacecraft propulsion is all about playing the game of how fast is it possible to accelerate the propellant such that it leaves the spacecraft at the highest possible velocity. And if you solve for then the mass of the propellant that you require, you can see that there's this exponential term where the specific impulse, so this is how fast we're expelling the matter, is on the denominator, right? So the higher this term, then the less propellant that we need to expend. Okay, so this brings me to the next concept, is I deal with something called plasma propulsion. So maybe we answer a basic question. Well, what is plasma? And why would we want to propel something with plasma? Why not just use a conventional chemical rocket? Okay, so I'll start with the first one, which is, well, what is a plasma? So a plasma is a state of matter in which the electrons and the ions become dissociated. So they are moving independently of one another. They aren't bound together like in conventional matter. So you can imagine if we heat something up, it will traditionally go from solid to liquid to gas. If you keep heating the substance enough, eventually the electrons will break free of the orbital cloud of the atom, and the electrons will move independently of the ions, which will have an opposite charge to the electrons. So plasma is naturally occurring in nature and is in fact the most abundant source of matter in the universe. And this is because, of course, the sun is a big ball of plasma. The thermal energy of the sun is enough that the electrons have moved free of the ions, and they're both independent of one another. Plasma also occurs naturally on Earth. So when you see lightning, this is an example of plasma created with intense electric fields and flows of current. We have many, and also the aurora borealis. This is plasma created from high-energy electrons trapped in the Earth's magnetosphere that bounce between the poles. And as those electrons enter into the atmosphere in the polar regions, they create plasma by ionizing the atmosphere. We can also create many man-made forms of plasma. So if you have fluorescent lights, if you have these plasma globes, this is using electric fields in order to create relatively low temperature plasmas. For the purpose of lighting, for the purpose of entertainment. You might have heard of plasma screen TVs. Those are examples of using plasma to create light and patterns like televisions. So when we talk about plasmas, we can map them out in terms of the density of the plasma. So this is how dense the plasma is and how energetic the plasma is. So this is the temperature of the plasma. So if you look at something like the sun, you have something which is extremely dense and extremely hot, right? So this is the inside of the sun. So if you have then useful plasmas in society, we're looking now in terms of fusion plasma experiments, and this is with the goal of creating energy. So these fusion plasmas are very, very hot. right? Even hotter than the inside of the sun, which many people would find surprising. However, you can see that they're much less dense than the inside of the sun. In fact, they're much less dense even than the atmosphere of Earth by orders of magnitude. And so these fusion experiments rely on very diffuse plasmas, so very low pressure plasmas that are extremely hot. And you can see now fusion experiments are getting closer and closer to this fusion goal of creating something hot and dense enough to create power. So this isn't the sort of plasmas that we use to propel spacecraft. Actually, plasma propulsion for spacecraft fits in a different category altogether. It's where the plasma is very diffuse, so this is a very low pressure plasma, and it's also very low temperature, right? So you can see the temperature is low and the density is low. And so this is the sort of plasmas we use to propel spacecraft. The reason why we choose something which is low density and low temperature is that we don't want to put a lot of energy where we don't need it. We don't want to put energy into making the plasma hot. We want to put energy into accelerating the plasma at high speed out of the vehicle, because that's what gives us the benefit in terms of mass savings. So how can we use then a plasma in order to generate propulsion? Well, we need to accelerate the plasma somehow so it exits at high velocity from our spacecraft. And there's three ways that we can go about doing it. The first is sort of the most primitive way, leads to the lowest performance. And this is if we just use the thermal properties of the plasma, we call this electrothermal propulsion. So for example, in an arc jet thruster, they create a plasma and then they expand the plasma through a diverging nozzle. So this is the same equivalent as if you're dealing with a conventional chemical rocket. You react a fuel and oxidizer in a chamber, and then you compress and expand that gas through a converging diverging nozzle, and you convert the heat into directional momentum. So you can do the same thing with a plasma. So with an arc jet thruster, they heat a plasma and they expand it through a physical nozzle, and this will generate thrust on a spacecraft. But it generally does it with quite low efficiency, so something equivalent to a chemical rocket. The reason why plasma is very interesting is because it's electrically charged. So if we move down to electrostatic propulsion, remember that electrons will have a negative charge and ions will have a positive charge. So if you put an electric field, so for example, created between a set of grids, you can accelerate the positive charges through those grids through the action of an electric field. So not something like a physical nozzle, but actually something created with a voltage difference between two plates which are separated over a short range. Those ions, once accelerated, you can neutralize with a beam of electrons, which takes care of the charge of the outgoing beam of ions. And using this electrostatic forces turns out to be much, much more effective than expanding gases through a physical nozzle. So you're able to achieve tremendous exhaust velocities using electrostatic means of propulsion. So the final way that you can act on a plasma is through something called the Lorenz Force. So this is a combination of both an electric field and a magnetic field that act in combination in order to produce a bulk force on an electrically charged substance. So for example, a plasma. So here you have a flow of current and a magnetic field that gives rise to a cross-field force, a Lorenz force, to accelerate plasma to extremely high velocities using these field effects. So this has nothing to do with converting thermal energy into momentum. This is all about applying a combination of an electric and magnetic field to produce a bulk acceleration of the plasma. Okay, so where does electric propulsion, plasma propulsion fit in terms of overall spacecraft propulsion? And I think this is a really important point that a lot of people miss in the first instance. So on the bottom, you can see that the horizontal axis is the amount of thrust that you're able to produce. And the vertical axis is the specific impulse. which, remember, the higher the specific impulse, the more efficiently we're increasing the velocity of our spacecraft compared to how much propellant we're using. If you have a conventional chemical rocket, you can get arbitrarily high amounts of thrust. So you can have your thrust increase to whatever value you might want. But there's a limit in terms of the specific impulse that you can do that with, because it's reliant on the chemistry of the reaction and also the mass of the exhaust products. So there's a certain limit in terms of specific impulse that you can obtain. Electric propulsion has another limit, but it's not a limit so in terms of the specific impulse. So the specific impulse can be much, much higher than with chemical rockets, but it's limited in terms of the amount of thrust that you can produce. And the reason is quite simple, actually. It's the amount of power that you're able to supply to the plasma limits the amount of thrust that you're able to produce, because it takes electrical power in order to accelerate the gas. And there's only a limited amount of electrical power that you're able to generate on your satellite platform. And there's then a simple equation, which I'll show you in a few slides' time, that allows you to calculate what is the maximum thrust I could produce based on the specific impulse that I need to produce that thrust at, given a certain power limitation of the platform. So it isn't a case that electric thrusters are somehow better than chemical thrusters. They certainly save a lot of fuel, but they can't get the high levels of thrust that you can with chemical rockets. So this is why the world actually needs both types of propulsion. You need chemical propulsion for those circumstances where you have very high thrust, and you need electric propulsion for those circumstances where you need very high specific impulse. And neither of these two systems alone can accomplish both tasks, which is why you need both systems. So just a bit of history to electric propulsion. The field of study has actually been around a long time, so dating back 100 years now. It was originally first proposed in the early 20th century by a combination of Tsiolkovsky, Goddard, Kontrachyuk, and Oberth, who proposed this idea of taking electrical power and turning it into momentum of a gas or ionized substance. So from the theory then, they developed the first electrothermal thruster around the 1930s, and that was developed in Russia. And they were already starting to look at the use of electric propulsion for real space missions by Stollinger in the around the 1950s. The first time that spacecraft electric propulsion plasma thrusters were actually used on space missions was in the 1960s. And the first device to be used was something called a pulsed plasma thruster, a PPT. And that was flown in 1964. More recently, they used electric propulsion for commercial spacecraft systems, whereas previously they'd only been used for military spacecraft applications. And that was in sort of the late 1990s. And the first use on a Deep Space One satellite of an ion thruster was in 1998. Okay, so just to give you some idea of these terms that I've been throwing around. So first, what is a Lorenz force? So a Lorenz force is a force that you can exert on a charged particle, which is directly proportional to the electric field. So it's aligned with the direction of the electric field. And it's on the cross product direction between the velocity of the particle and the magnetic field. So this is also equivalent to the flow of current cross product with the direction of the magnetic field. And so this is the overall Lorenz force, which acts on each particle individually. And you can see from the sign, so this term Q in the Lorenz force equation refers to the particle charge. And so the Lorenz force will act differently on negative and positive charged particles. So if you have a negatively charged particle in a magnetic field, it will tend to rotate one direction, whereas a positively charged particle will tend to rotate the other direction, right? So you have positive charged particles rotating here clockwise, and negative charged particles rotating counterclockwise, with a magnetic field which is going into plane, so through the presentation. However, the E cross B direction, right? So this is if you have an E field pointing in a direction perpendicular to the B field, it introduces a Lorenz Force term, which acts the same direction on both negative and positive particles, even though those particles are gyrating in different directions. So you can see here, the negative particles are revolving counterclockwise, positive particles are revolving clockwise, but they both drift in the same direction and with the same magnitude. So that's what we refer to as a crossed field drift. And this will become important, by the way, when I'm explaining the concept of how does a Hall effect thruster work. Okay, so if we're talking the performance parameters of a electric propulsion system, a plasma thruster, a lot of these are exactly the same as with a chemical rocket, which is the theory I introduced previously. So we have that the overall thrust is equal to the mass flow rate times by the exit velocity of the system, where now the specific impulse is just given simply as the exit velocity normalized by the gravity constant G. So this is almost the same equation that I introduced previously. The difference is that there is no pressure force term. There's only a term associated with the particle momentum, because the pressure for these very low pressure gases can be completely neglected. So in some sense, these equations are even more simple. There is one very important additional equation, though, when you're talking about plasma thrusters, is the thrust efficiency equation, which is this one on the bottom, which is about the idea of converting electrical power into momentum. So we define an efficiency which is equal to the beam power, so this is the work that we're getting out of the system, divided by the total power that we're putting into the system electrically. So you can imagine, like any efficiency equation, you can never get an efficiency higher than 100%. So if you put in 100 watts of power into a system, you can expect that only some fraction of that power is turning into the beam energy coming out of the system, right? Electric thrusters will tend to operate at efficiencies maybe between 50 to 70% total efficiency. So they're quite efficient, but that means we're losing some power that we put into the thruster, either thermally or through the light emitted by the plasma or through electromagnetic radiation or something. So if you take this equation for the thrust efficiency and you solve for force, right? So this is the thrust produced by the system. You see that it's inversely proportional to the exit velocity v. So it's inversely proportional to the specific impulse, and it's directly proportional to the power. So this means the more power we have, the more thrust we produce. But the higher the specific impulse, then the less thrust we produce, right? So this allows you to then trade off what is the advantage of having higher specific impulse and saving mass versus having a higher level of thrust and producing more force on your satellite. Okay, so I'm going to go through quickly some of the main types of electric propulsion that are around today. There's really two major types. It's the gridded ion thruster and the Hall effect thruster. So I'll start with the gridded ion thruster because it's a bit easier to explain. So this is an electrostatic type thruster where you're accelerating ions by accelerating them through a potential difference. So this is a set of grids which are closely spaced together, and you create a different voltage on each of the grids, and it accelerates ions between them through small holes. So there's a subcategorization of ion thrusters depending on how you're creating your plasma. So radio frequency ion thrusters use RF power in order to heat the gas and create a plasma. Microwave ion thrusters use very high frequency signals, so microwave signals, in order to create a plasma. And electron bombardment ion thrusters, called Kaufman ion thrusters, use DC electric fields in order to create the plasma. So depending on how you create your plasma, here's a little sort of schematic cartoon on how you would actually create the thruster. So you produce a plasma within a channel, within a cavity, and you're continuously feeding in propellant in order to replenish the ions which are leaving the system. So you have some sort of a gas feed line, gas comes in, you ionize your gas to create a plasma. And then you have an anode here, and the purpose of the anode is to bias the plasma to a high electrical potential, so on the order of thousands of volts. Then you have grids here, so these are your acceleration grids, where you go from 1,000 volts, which is your plasma potential, down to 0 volts, which is your cathode potential. And as the ions pass through these grids, they're accelerated by this potential difference, by this electric field, and they exit the device at very, very high velocities. So for every ion that leaves the system, if it has a charge of +1, you need to also supply one electron with a charge of -1 in order to balance the overall charge of your system. Because if you only had ions leaving your system, you would rapidly accumulate charge on your spacecraft, and the ions would literally turn back and travel back towards the spacecraft because of this charge difference. So this is the purpose of having these cathodes, electron sources, is to create an equivalent number of electrons to chase the ions downstream that are leaving the system. So this is sort of my simple cartoon of how they work. This is a cutaway view of an actual Kaufman type ion thruster, so you could see some of the details of how they work. So here you have your propellant flow inlet, comes through here. You have a baffle just to help distribute the flow. Similarly, you have flow entering through the center, and this here is a hollow cathode, which generates a sea of electrons, so it pre-ionizes the gas. Then you have this red structure along the outside, which is your anode, which biases the plasma, and a magnetic field. So this blue structure here is a magnetic circuit, which creates a magnetic field in order to confine the electrons within the body of the plasma to enhance the ionization rate. Then you have these grids here, closely spaced, where you have a screen grid, which is at the same potential as the plasma within this cavity, and an Excel grid, which is very close to 0 volts, which is your voltage on the outside of the spacecraft. And this is your cathode located to neutralize the beam. So it's located outside of the thruster itself. So the ions are accelerated through these small gaps in the screen and neutralized by this beam of electrons coming from this cathode off to the side. This is what they look like physically. So this is the T6 ion thruster, which was developed in the UK at a company called Kinetic. And this is one of the NASA great big huge ion thrusters. You can see somebody standing here sort of to give this thruster scale. Notice that it's sort of transparent, and that's because these grids have very tiny holes in between them. The holes are kind of on order of like a millimeter diameter, and the grids themselves are spaced at sort of sub-millimeters apart. So they're very, very closely spaced grids to create this electric field. So then the next type of thruster I'll talk about, which is more my background, so this is what I did my own PhD on, are Hall effect type thrusters. And gridded ion thrusters, which I was talking about previously, those were developed predominantly in the West, so in America, whereas the SPTs, these are the Hall effect thrusters, they were predominantly developed in the Soviet Union during the Cold War days. So this was sort of the competition to the US thrusters. So they're referred to as stationary plasma thrusters in the literature, abbreviated SPTs. Honestly, there's not really a good reason why they're called stationary plasma thrusters, because all plasma thrusters are more or less stationary. So this is sort of just historical reasons that lead to the naming. They're simpler devices mechanically than gridded ion thrusters, but the physics is a little bit harder to understand. So they're composed of three main components. You have a ceramic channel, which here is like it's a coaxial ceramic channel, so an annulus around the thruster. Then you have solenoids, so these are electromagnets that create a radial magnetic field. And a cathode, which is located external to the device, so you can see the cathode up here. And the purpose of the cathode is to neutralize the beam of ions which is formed by the device. So let's explain now the physics. So it's a very simple mechanical device, but the physics is a little bit hard to understand. So starting from the cathode, you have electrons which are coming out of the cathode, drifting into free space. And at the base of the channel, you have your anode and gas distributor. So the electrons normally want to work their way from the cathode to the anode. So they start to drift into the channel and try to drift back towards the anode to complete the circuit. However, there's a radial magnetic field, so a magnetic field that is pointing towards the center, which causes this Lorenz drift of the electrons. So the electrons start to orbit around the channel because they're being driven by that Lorenz Force term that I mentioned previously. So the electrons then become trapped in an orbit around the channel, and those electrons start hitting the gas which is coming from the anode. So every time an electron then strikes one of these neutral gas atoms, it could ionize the atom, so that kicks off an electron from the atom. And that electron then also becomes trapped in this orbit around the channel. And this creates a cascade of electrons that all start to orbit around the channel, which is being sort of fueled by the propellant, by the gas which is coming in. So if you go back to the picture, it creates this intense amount of ionization right at the exit of the channel, where all of these electrons have become completely trapped. The ions, meanwhile, have become free of the electron, and because they're much heavier particles, they're not as influenced by the magnetic field. So they don't experience a Lorenz force, they only see the action of an electric field, which is propelling them out of the channel. So they move in the opposite direction of the electrons. The electrons are struggling to work their way towards the anode, and then therefore the ion beam is moving in the opposite direction. And it forms this nice, pretty sort of plume out of the back of the thruster. So yes, hopefully that makes some sense, but I will admit, even when explaining this to my students in third, fourth year university, this takes a little while to sort of get your head around the physics of these devices. So physically, this is what they look like. Actually, they're much, much smaller than gridded ion thrusters because the density of thrust is much higher. So they're about, if you look at my image now, they're about maybe this big in diameter. So relatively easy to pick up and handle, as opposed to gridded ion thrusters, which, you know, were the size of a small table. You can see that these thrusters here have two hollow cathodes. That's just for redundancy in case one breaks. You don't need two hollow cathodes. The white material is a ceramic channel, and the electromagnets are located in the core and off to the periphery of the thruster. And at the base of the channel is this metallic anode plate, which is just an electrically charged plate with little holes drilled into it, which allows the propellant to diffuse into the channel. And you can run virtually any gas you could think of through a Hall effect thruster in order to create a plasma and accelerate the ions from it. Whereas for gridded ion thrusters, they're quite highly tuned to the gas that you're using. So Hall effect thrusters have this advantage that they can sort of consume any propellant you might choose. Okay. So those are the two pillar technologies that we have in electric propulsion today. So I just wanted to talk now a little bit about the research that I'm doing in my group and the sort of challenges that we're trying to address. So here's what I consider two of the big challenges facing the space industry today. One is the challenge of access to space. So this is the environmental impact of launch vehicles and in-space propulsion, right? So as we send more and more objects into space, we have to start being conscious of the environmental footprint that we're having on our planet by these propellants. Then the next topic is the idea of space debris. So once you launch an object into space, it will sit there and linger in orbit for a very long period of time. And because nothing is actually removing objects from orbit, our space environment is becoming more and more littered with debris. So this could be old satellites, pieces of launch vehicle fairings, bits of paint, nuts and bolts, those sort of things. According to ESA, right now we have, well, hundreds of millions of objects, which are between 0.1 to 1 centimeter in diameter, almost a million objects between 1 and 10 centimeters diameter, and about 34,000 objects greater than 10 centimeters in diameter. And the numbers are only growing because nothing's actually removing these objects from orbit. So it's a big and a growing problem. So over the next 10 years, there's going to be even more proliferation of objects in space. So we're going to grow from about 4,000 active satellites to more than 10,000 active satellites. So i.e., there's more satellites in the next 10 years compared to all of the satellites in all of human history. And this is being driven by what we call mega constellations from companies like SpaceX and OneWeb, who are trying to do satellites for persistent internet coverage in space. So they're launching thousands of satellites into orbit over the next 10 years. All of those satellites have plasma propulsion on them. In fact, every single one of those satellites uses Hall effect thrusters, right? So the idea of the research that I'm doing is saying that there's so many Hall effect thrusters, which are going to be flown in the next 10 years, we have to start being very, very careful about the sort of propellants that we're using with those thrusters, right? So this is what I see as sort of one of the major issues. Additionally, if you're looking at launch into space, so this is access to space, there's going to be, I think, a dramatic increase in things like space tourism. So right now, the total number of humans in space is somewhere around 553. And over the next 10 years, this is going to rise to thousands of people having been to space either recreationally or for work or for science or for some purpose. And so we have to start considering environmental considerations. So right now, the main fuel for Hall effect thrusters and gridded ion engines is Xenon. And Xenon is very, very costly in terms of energy cost in order to produce. And the reason for that is Xenon is a very scarce substance, and the way that we produce it is to liquefy it out of the Earth's atmosphere. So we take a large volume of air, we refrigerate the air until it turns into a liquid, and then we use a successive liquefaction and refinement in order to pull the Xenon out of the air. And that's very energy intensive. So we're spending a lot of energy creating fuel for these Hall effect thrusters, which are going to be thousands and thousands in scale. So the way that I see then the role of my space propulsion research is to solve some of these big challenges. So sustainable access to space without adverse environmental impact, using in situ resource utilization for deep space exploration rather than bringing propellants from the surface of our planet. So for example, harvesting propellants outside of the Earth, either on the moon or on asteroids or somewhere, where we don't have to pay the energy cost to haul it into orbit, and we don't actually have to invest the energy on the ground in order to create the propellants to begin with. And also looking to ensure that all spacecraft can remove themselves and their debris from orbit in order to make way for the next generation. So we need technologies to do with debris removal. We need to make sure that the spacecraft are equipped with enough propulsion that they can safely remove themselves at the end of life. So at the same time as like trying to accomplish these challenges, we can't lose sight of what space is already providing to us. So we need to meet humanity's need for finding resources outside of our own Earth in order to sustain our growth as a species without jeopardizing the planet. And in order to do that, we need space and we need space technologies, right? So it's not a question of just saying, well, maybe we'll do less access to space and this will solve the problem. No, not really, because actually we need to access space in order to accomplish these goals that we want to as a species of not hurting the planet. Okay, so that's the problem. So I'll show you some of the research going on then in our group trying to address these problems. So one of the big themes of my research group is the use of water as a propellant for future spacecraft propulsion. So I'll start with this simple schematic on the right-hand side. You have a tank of water. So this is just regular liquid water. You send it through an electrolyzer in order to generate oxygen and hydrogen streams. The hydrogen stream you send to the external cathode. So remember, this is the neutralizer, which produces electrons to neutralize the ion beam. And you send your oxygen through a Hall effect thruster stage in order to generate your plasma, and it's oxygen ions then exiting the system, being neutralized by the hydrogen effectively. So why would you do it in this way? The reason is that the neutralizers themselves, so these are the cathodes, are very, very sensitive devices, and they're sensitive against materials like oxygen, liquid water, nitrogen, anything that could potentially chemically contaminate the emissive insert. So this is the thermionic material responsible for generating the electrons. The one material that these cathodes really, really like is hydrogen. So that's why we pull the hydrogen stream in order to power our cathodes. Why do we move the oxygen to the Hall effect thruster? Oxygen is the heavy gas here, right? So if you look at the atomic mass of oxygen, it's much, much heavier than the hydrogen, which gives you a favorable amount of thrust in comparison to the velocity of the ions which you're creating. So this is sort of the architecture which kind of makes sense when you're dealing with water as a propellant. So then the picture gets more interesting when you say, but if you're creating oxygen and hydrogen from an electrolyzer, why can't you also burn those propellants in a conventional chemical rocket when you need high thrust, right? So here we've added on slightly to our architecture. And we say, okay, we can fill up plenum tanks of hydrogen and oxygen in situ, so you electrolyze your water. And you can use that either when you need high specific impulse, so for the electric propulsion, or if you need high thrust maneuvers, you can use it for a chemical propulsion stage. And in fact, hydrogen and oxygen is about the best propellant combination you can hope for, in terms of the mass of the exhaust products, in terms of the energy of the hydrogen-oxygen reaction. It's a very favorable propellant for in-space propulsion. So we have two separate activities within the group, one looking at this electric propulsion part, and one looking at the chemical propulsion part, both being fueled by oxygen and hydrogen streams. So then the picture can become even more interesting. So let's suppose that you have your water and you put that through an electrolyzer to produce hydrogen and oxygen gas. Well, I'm sure you guys might have heard of fuel cells, right? So what a fuel cell does is it takes hydrogen and oxygen and it converts that back into water, releasing electrical energy. So this is effectively acting like a battery, and it's known as something called a regenerative fuel cell cycle. And this is something that ESA, so European Space Agency, is already looking at these regenerative fuel cell cycles as a way to deal with the energy requirements of the satellite platform. So instead of using lithium-ion batteries, you can use this regenerative fuel cell cycles to give you much higher energy storage density on your platforms for the really like next generation satellite platforms. So then it's like, well, this is great. Because what if you combine a regenerative fuel cell cycle, which is giving your power requirements to your satellite, combined with, solar panels to actually generate the power to begin with. This just acts as an energy storage. But it also then feeds an electric propulsion system. It also feeds a chemical propulsion system. And you can even tap off of your hydrogen tank in order to provide reaction control thrusters. So these are the thrusters to do with attitude control of your satellite. And you can have a whole satellite architecture built entirely out of using water. So why is water great? Well, it's been used for a long time. So water fuel cells date back to the Gemini and Apollo mission. So there's a lot of existing space expertise in using these systems. They store up to 4 times the energy density of lithium-ion batteries. So they're very good power consumption-wise. And so then this whole architecture can be fueled purely with water. Water is very low cost. But more importantly, you can find it on planetary bodies like the moon and Mars and asteroids, right? So this gives you the prospect of using an in situ materials from wherever it is you're exploring. Okay, so remember I said that we're looking at these two, the electric propulsion system and the chemical propulsion system within my lab. So this is the first one, what we call the wet head. So this is the water electrolysis Hall effect thruster, where we've built and prototyped a Hall effect thruster to operate off of oxygen and hydrogen streams. So this is just a picture of the Hall effect thruster firing. You can see here what it looks like, kind of a greenish tint to the beam when you don't have a magnetic field applied. And it turns to sort of a purplish, bluish color when you apply the magnetic field and confine the electrons here. In terms of its performance, so we've developed up to 38 millinewtons of thrust. That's a very, let's say, small number in the grand scheme of things. So imagine if you put a small coin in your hand. The weight of that small coin would be approximately the same as this 38 millinewtons of thrust. So it's a tiny, tiny amount of force. But the idea of Hall effect thrusters is that you apply a tiny amount of force for a long amount of time, and therefore the total impulse that you've applied is nevertheless very large. The important number for us, though, is the maximum specific impulse that we've tested. So we've tested it up to about 4,110 second specific impulse. And if you're using xenon as a fuel, the specific impulse is around 1,550 seconds, much, much smaller than this 4,000 seconds that we've created. So what does this imply? Remember, the specific impulse tells you how much fuel you need for a given change of momentum of your satellite. We have nearly 4 times, well, 3 times as much specific impulse, which means that this leads to huge mass savings for the satellite platform compared to Xenon. However, there is a drawback. So far, the maximum thrust efficiency that we've measured is about 15.5%. And this compares to over 50% for a xenon Hall effect thruster. And the fact is that xenon is much, much easier to ionize, which is why it's been the preferred fuel for so long. So this means that we require more power in order to accomplish the same amount of thrust for a given mission, right? So this is, let's say, the main challenge that we're addressing is how high can we push up the maximum thrust efficiency? But I can tell you, talking with our commercial counterparts, even 15.5% is a workable number when they start looking at the amount of money savings versus xenon fuel, right? So just based on cost issues alone, they're very happy to switch to water. To give you an idea, you would typically be spending for your fuel costs for a satellite mission on order about 2 or 3 million pounds for the cost of the xenon, versus water at the same amount, which would be, literally pounds, not millions of pounds, just because of the much, much cheaper nature of water. Yes, and so the poor efficiency of using water we attribute to a small ionization cross-section. So this means that the oxygen molecules are physically much smaller than a xenon molecule. So they're a lot harder to hit and ionize with electron bombardment. And also we lose energy to modes that you wouldn't in xenon, because xenon is a single atom, whereas oxygen is a molecule. So the oxygen molecule can vibrate, it can rotate, it can dissociate, and all of those different degrees of freedom will take energy out of the system. So in some way, the poor efficiency is a fundamental limitation of using a lightweight molecular propellant. So there's only going to be so much that we can stretch the thrust efficiency. And then we have to see at the system level, can we live with that disadvantage for the advantages that it brings? So then this is the second part. So this is using hydrogen and oxygen in order to generate chemical thrust, right? So literally burning the propellants. And we're doing that in kind of some clever ways. One of the reasons why hydrogen and oxygen electrolysis thrusters haven't gained so much traction to date, even though the concept seems quite easy, is if you have a stoichiometric mixture of hydrogen and oxygen, so this is in the same proportion that you separate it from water, the reaction is so energetic that the heat that you generate will melt almost any conventional material. So there's this big problem that if you're using hydrogen and oxygen thrusters, you're going to like melt and erode away the thruster itself very quickly. So we've been addressing this, I think, in quite interesting ways. One of the way is to go super, super small scale with the size of the thruster, such that we can balance the thermodynamics of the system to reduce the wall temperature, but still maintain the efficiency of the reaction. And what we've been looking at is the use of microelectrical mechanical systems, so MEMS technologies, so to produce thrusters using the same techniques that you would produce silicon chips. So you can get ultra small scale with the thermodynamics. And also to use something that a layer of iridium, which is a platinum group catalyst metal, in order to facilitate the reaction between the hydrogen and the oxygen, so that instead of burning the propellants, what you're doing is you're reacting the propellants in a very controlled way on the micro scale, not allowing a free flame in order to develop in any conventional sense. So these thrusters are almost like little chemical factories, not like burning a propellant in a macroscopic space and then trying to like converge and expand that propellant through a nozzle. So we call this the Iridium Catalyzed Electrolysis CubeSat thruster, or ICE Cube for short. And it's this microscale chemical thruster. So what we've been able to test in the lab so far is specific impulse of around 300 seconds, which is comparable to a conventional chemical rocket. Very small levels of thrust, but these can be kind of stacked arbitrarily. Like, so you would use many, many thrusters in order to get the value of thrust as high as you might want. Yes, these are inlet pressure, chamber length, just for reference. One of the cool things about these thrusters is because you're producing them on silicon wafers, you can produce many, many thrusters on the same run, right? So here we have a set of 31 thrusters fabricated on each 4-inch wafer set. And this gives you a huge degree of flexibility if you're doing experiments, because you could be changing all sorts of different parameters between those 31 thrusters and then test multiple design configurations. And at any time, you're only working with a single silicon chip. So it's produced in sort of batch runs. Just to give you an idea of how the MEMS approach works, you start with your substrate and a coating of what we call photoresist, and then you use a technique called photolithography to harden the photoresist in layers that you don't want to etch from your silicon. Then you use a technique called reactive ion etching to burn holes into your silicon substrate. And then we sputter deposit this layer of iridium, which is this metallic compound, over the surface of the device. and we lift off the photoresist, so the hardened parts, in order to produce our final sort of thruster. Now this is, let's say, 1/2 of a thruster. And so then finally you put the two halves over top of each other and use diffusion bonding to bond them together. And that leads to your final thruster chip. And we work with the London Centre of Nanotechnology, who has the instruments and machinery to actually do this MEMS process, leading to the final thruster chips. So I'm wondering, do I have any pictures of the thruster chips? Unfortunately not. So then I'll move on to the next one, which is our kind of high power variant of the same concept. So this is our Iridium catalyzed electrolysis larger thruster. And this one goes up to a thrust of 1 Newton and specific impulse of about 320 Newtons. And this one is much more conventionally sized compared to these micro miniature MEMS technologies in the previous slide. But you could see, even though I refer to it as a very large thruster, when you look at it compared to, let's say, size of a coin, it's still macroscopically quite small. So here's my PhD student, Charlie. He's holding the thruster in his hand. The hydrogen and the oxygen enters from the side. Sorry, the hydrogen enters from these branches on the side, and the oxygen enters from the base. And this is just a picture of the stand. So you put the thruster itself on this stand, and that is the mount where the thruster is mounted in order to be either on the satellite, or in this case, we put it on a thrust balance inside the vacuum chamber. The way that we manufacture these larger thrusters is a little bit different than the MEMS technique I described before. What you do is you take thin sheets of metal and you use like water jet cutting or laser cutting in order to cut these patterns out of the sheets. Then you lay the sheets on top of each other, so one stacked on another. And then you use diffusion bonding, which is an application of high stress load and high temperature in order to weld these sheets together. And then you use a laser cutter or water jet cutter in order to extract the thrusters physically then from the material. So this is actually my last slide because I wanted to end with sort of a snapshot of where we are. So on the water electrolysis Hall effect thruster, the wet het side, actually we've done quite well in getting kind of all of the experimental data that we want out of the system. And now we're working with commercial partners creating the flight model version of that same system. So this one is more or less in a very good place. The ice thruster, which is this one that I showed the pictures of in the previous slide, this is right now work in progress because we've just started to collect our first measurements of the system. And there's still a good deal of work to go in order to characterize the performance of the thruster over a wide range of operating conditions before it can be then scaled up into, let's say, a commercial program. Yeah, so that's where we are now. And yes, thank you for your attention and good time for questions and answers. Okay, and I see, yes, we have some questions on the chat window. So does somebody want to dictate the questions to me so I could focus on moving to the right point in the slides? And
yeah, sure. So the first question is asked by Mayank Sharma. He's asking, in the equation slide 11 and 12, we have assumed G to be the constant. Shouldn't it vary with respect to the height ascended?
Yes. Okay, so it's a very good question, and a common source of confusion is the use of this normalizing constant G. Okay, so by convention, we choose G to always be G at Earth gravity condition sea level. So this is 9.81 meters per second squared, always, doesn't change. And it's just a convention of how we've defined this unit. Okay, so G does not vary depending on where in the universe we happen to be applying the term specific impulse. It's just by convention. Truly, instead of talking about specific impulse or G, what we're really referring to is this constant C, which accounts for the momentum and pressure forces we're producing from our rocket. The term specific impulse is sort of a human created term that we use in order to just compare technologies against each other. It's always referenced to Earth gravity G.
And the second question was asked by Shaunak Banik. He asked which propulsion would be more efficient, the grid propulsion system or the Hall effect propulsion system? What are the drawbacks of both?
Okay, so the gridded ion thrusters are nearly always more efficient than the Hall effect thrusters, if I go to them. So these gridded ion thrusters typically exhibit thrust efficiency up to maybe 70, almost 80% thrust efficiency. Using the exact same propellant, the Hall effect thrusters have a much lower thrust efficiency. So here, a Hall effect thruster will typically have a thrust efficiency of around 50 to 60%. Also, the specific impulse of a Hall effect thruster is lower than a gridded ion thruster. So it seems that it's losing on specific impulse and it's losing on thrust efficiency. So then the big question is, why are Hall effect thrusters the main form of electric propulsion used today and not gridded ion thrusters? Because I can tell you of all the flying technologies, Hall effect thrusters are by far the more popular. The reason for that is quite fundamental. So take a look at this guy standing next to this gridded ion thruster and think about how big and how heavy that thruster weighs. Okay? The Hall effect thruster you can hold in your hand. It's a very tiny device and it produces the same amount of thrust. Hall effect thrusters are much smaller, they're much lighter weight, they have fewer components, less parts to break. They also operate at much lower voltages. So from a spacecraft manufacturing standpoint, Hall effect thrusters are by far the winning technology because of all of those other considerations. However, if you're looking at specific impulse and you're looking at thrust efficiency, then you would normally choose a gridded ion thruster to get the job done. Okay, so I think, yeah, very good question, very complex answer because it depends on a lot of things that aren't necessarily just the performance of the system.
So guys, you can unmute and ask any question if you want. Nishant, if you're able to unmute, like if you're comfortable to unmute, you can ask her.
Yeah, we can have Nishant, and then Vikram also had a question. So are you guys able to unmute?
Okay, Nishant is saying he has a noise.
Yeah.
So Vikram, you can go forward and
Yeah, go ahead.
Right. Good evening, Dr. Aaron. I've read some of your works on Google Scholar and I found them truly intriguing. I'm a big fan of your works. I just had one question. How efficient is a solid propulsion, that's combustion reaction power thruster, and can it generate more momentum and thrust than the plasma propellers you've talked about today?
Yeah, so solid propellants, normally those are composite rocket motors. They tend to have specific impulse of around, let's say, 200 to 250 seconds or so. You can generate as much thrust as you might want from a solid composite motor. In fact, if you think of the solid rocket boosters that are on side of the space shuttle, those were composite solid motors, right? So they could produce hundreds of thousands of newtons of thrust without trouble. The drawback of solid propellants is that the specific impulse, so let's say 240 seconds, is much lower than the specific impulse of hydrogen-oxygen engines. So let's say the space shuttle main engines, which have a specific impulse above 300 seconds. And because specific impulse has such a dramatic impact on the amount of momentum you're able to give to the vehicle given the propellant weight, then this is why people tend to use liquid propellants for the launch vehicle stages, not solid motors. Solid motors are normally used for boosters.
Yeah, thank you.
So even I'm sorry.
Mhm.
Does someone want to ask a question?
Yeah, Samruddhi.
All right. You go ahead. I'll ask after you.
So, Professor, I was just thinking, like, eventually the plasma potential's thrust is very less. Like, so while using them in the military services, like, can they be actually be used because military jets eventually require higher thrust? So, like, is it actually possible to be used there in the Earth itself, like using it in the military jets? Like, eventually the thrust is very less.
Sorry, just so I understand the question, are you referring to the like whether or not they could be used like within the Earth's atmosphere and not just in orbit, or are you referring to like their use generally for the space engineering?
Generally for military jets.
Well, for military, okay, so I should clarify something. So far, spacecraft electric propulsion, so plasma propulsion, is only used in orbit. So this is once we've already left the Earth's atmosphere and once we're in space. And the reason for this, there's two big reasons. The first reason is that the amount of thrust that they produce is very, very small, right? So remember I said it's in millinewtons level, which is like the weight of a coin in your hand. So this is fine if you're already in orbit because you could produce a very small thrust for a long time, but it's not going to be convenient if you're trying to launch something into space where you need a large amount of thrust. The other reason why you can't have these plasma thrusters working in Earth's atmosphere is Earth's atmosphere is much, much too dense. So the necessary pressure of the propellant in order to generate these plasmas efficiently is very, very low and very rarefied compared to the high density of Earth's atmosphere. So if you tried to work these technologies outside of a vacuum environment, they just wouldn't work. And the reason is that all of the electrodynamic processes that we're relying on are being overwhelmed by the collision of neutral particles with the electrons, which cloud everything. And then the electrons aren't allowed to move in complete orbits and experience these Lorenz Force effects because they're constantly being bombarded by and bombarding into the atoms that make up the atmosphere. So they don't work outside of vacuum conditions.
So, sir, I actually had a question about the Lorenz force. So
Mhm.
you mentioned that it's caused when the electric and magnetic fields kind of become perpendicular to each other.
Yeah.
So my question is, are they in a way produced by electromagnetic waves? Because electromagnetic waves are also caused by perpendicular electric and magnetic fields, right?
Yeah, the concepts are related for sure. So you can have electromagnetic waves which propagate through plasmas, and the way that electromagnetic waves propagate through that charged medium is different than when they're propagating through free space, right? So you can have perpendicular electric and magnetic fields, and actually the angle between the electric and magnetic fields can actually change as you pass through plasmas. And the phase offset also changes, and their just general propagation dynamics change, right?
Okay.
So that's one thing. Generally, Lorenz forces, they're not, let's say, speaking about wave propagation. They're talking about more or less like DC phenomenon, which are occurring within the plasma bulk. So this is deliberately applying static electric fields and static magnetic fields, which are perpendicular to each other, right? But continuously over time. So the electric fields would be created by charged plates, like metallic plates that are held at different voltages. And the magnetic field is created by solenoids. So these are electromagnets that are created with windings of magnet coil.
Coils, right.
Yeah.
Thank you.
Yeah, hi,
Maybe you
Mr.
can
Knoll.
unmute.
Yeah, I know. Yeah, hi, Mr. Knoll. So basically, I have a question regarding nuclear thermal propulsion, and so like it's expected that the current rockets, so it could it could allow the current rockets to reach the speed of up to 4.9 miles an hour. Sorry, a second. So what are your views on that?
Yeah, so you can see actually nuclear propulsion falls somewhere in between electric propulsion and chemical propulsion. So it's able, because you have an abundant source of energy, it's able to also go to arbitrarily high thrust, right? So very, very high thrust. But it also is limited in terms of specific impulse because you're reliant on a thermal expansion of a gas. So normally with nuclear propulsion, you're talking about a propellant like helium or a propellant like hydrogen as being your propellant gas. And there's a limit to the temperature that you could raise the propellant before you can't confine it with, normal physical materials like chambers and nozzles. And so that limits then ultimately what is the specific impulse that you're able to create from the system, right? But it gives you a nice compromise between high specific impulse, electric propulsion, and high thrust chemical propulsion. So it's good for some interplanetary transfers. So I think NASA's looking into this. Also in the UK, the company Rolls-Royce is looking into this. Yeah. And so it could have quite an interesting future in the space industry in terms of helping to reduce the amount of fuel and helping to give larger, more ambitious transfers. But it won't reach the same levels of specific impulse performance as plasma propulsion.
Okay, thanks a lot.
Yeah. So, Professor, I wanted to ask, what are the components of the debris that is caused by iron thrusters, and does it have any chemical components, and what happens to those chemical components in the space, and should we be concerned about them?
For ion thrusters.
Yeah.
So generally, ion thrusters will use xenon as a fuel, right? Which is a noble inert gas, right? So once the ions are created and exited from the beam, even when they recombine with the electrons, they don't condensate and they don't form in and of themselves some sort of debris to the space environment. So I think in that sense, you don't have to be worried about the exhaust gases. I guess the biggest contributors to space debris when you're looking at missions using ion thrusters are the satellites themselves. So the satellites, the pressurized tanks, the computer instruments on the satellite, when the satellite ends its mission, all of those things become debris. And so the responsible thing to do is to make sure at the end of your satellite mission that you remove the satellite itself. And you have two choices. You can remove it into the Earth's atmosphere so that it burns up, or you can move it into something called a graveyard orbit, which you bump it higher into orbit, into the Van Allen belts, which is a radiation hot zone, where satellites aren't intending to operate. And then either of those cases, you've kind of removed it from where you would like to operate satellites in the future.
All right, thank you very much.
So my question is, are there any solutions proposed for space debris?
Yes, there's a number of missions proposed for space debris removal. I was kind of involved somewhat with a mission called Remove Debris, which is back when I was working with the Surrey Space Center. And the Remove Debris mission was to demonstrate debris removal technologies in orbit. And so they launched a spacecraft and they put out simulated targets like space debris targets, and then tried various technologies in order to capture and remove those debris. So they attempted harpoons, they attempted net capture. And they also tested proximity detection systems, like how well you could scan the characteristics of debris objects.
Okay.
I think there's also like a company called Astroscale, which is right now conducting a debris removal demonstration where they've also released a target. And then they have their satellite testing how well it could dock with the target and tug it out of orbit.
Yeah, so many of the debris are dropped in the ocean. So are there any other solutions other than dropping in the ocean?
Yes, so it depends on the characteristics of the satellite. But if you have a fully demisable satellite, when it re-enters into the atmosphere, it could be completely turned into plasma and gas so that nothing actually strikes the planet. If you're dealing with a larger satellite, then you'll want to put it in a controlled reentry down into the ocean, as you said. The other option is to put it into a graveyard orbit, where you boost its orbit higher such that it's inside the Van Allen belts. And so then it'll remain in orbit, but in an area of low interest for like future space missions.
Okay, thank you, sir.
Yeah.
Paresh, you can unmute and ask your question.
Yeah, Professor, so I was just thinking about how about replacing xenon as a fuel with halogens, like they're more popular, what I think.
Yeah, I think actually with halogens, they have been researching their use for future spacecraft missions, right? And one of the drawbacks, I guess, that they have to contend with is the fact that halogens are often very reactive with metals that could be used on the spacecraft. And so then when you're using these fuels, you have to be very careful about the material compatibility, right? So the tanks, also any sort of sensitive optical components, the satellite structure itself. But I know a lot of groups are looking at the use of iodine for electric thrusters because iodine is very easy to ionize. It stores well as a solid at very high density. And it has a very good ionization cross section. So it has a lot of advantageous features.
Okay, so just one last question. Like what like basic physics like we think I think is like we have read in the books is like does like when ions they actually start being in the engine, like does they lose their energy a little bit like before getting propelled out?
Yes, I mean, you give, let's say, energy to the ions by the electric field, which is normally right at the exit of the thruster, right? So when the ions gain the energy from the electric field, then almost all of that energy is carried out of the system efficiently. But when you're creating the plasma itself, you're giving the ions thermal energy, and you've also given it some potential energy from the fact that you've removed the electrons from the orbital clouds of the ions. Now, those sort of energies can be lost from the system when the ions recombine on the walls of the thruster, right? So as the ions collide with the channel walls, then they'll tend to then acquire back their electron and come back as a neutral particle. So you remove that energy from the system. And also physically, the ion's momentum is lost when it collides with the wall. And so these two loss mechanisms then take energy away from the plasma and account for some of the energy. Remember how I said it's never 100% efficient? It accounts for some of that energy loss of efficiency that you're getting overall.
Okay, and Professor, like we like you showed us a formula in one of the slides, but like force is like mass into VE, like that's the exit velocity.
Yeah.
So am I thinking like the exit velocity is the escape velocity?
No, the exit velocity is just that. It's the velocity at which the ions are exiting from the thruster. So it's the relative velocity between the thruster and the ions. It's different than escape velocity. So escape velocity, you're thinking of the necessary velocity to, for instance, escape a gravitational field like the Earth. And that's a very different concept.
Thank you.
Yeah, hi. Hi, Professor. Yeah, so my question is, like, we use magnetic field in both kinds of plasma propulsion. So is there any specific intensity ranges among the intensity of the magnetic field?
Yeah, so the magnetic field is usually between 100 Gauss to 300 Gauss in field strength. And the reason why you choose a magnetic field of that field strength is you want it to be acting on the electrons efficiently so that the electron gyro radius is very small, but you don't want to influence the motion of the ions. So you keep the magnetic field deliberately small so that you're not magnetizing your ions. Right? So how strong is a magnetic field 100 to 300 Gauss? It's actually very, very weak. So if you have like a refrigerator magnet that sticks onto your refrigerator, on the surface of that magnet, you probably have a magnetic field strength closer to 800, 900 Gauss. right? So this is much higher than the magnetic fields that we use in the thrusters. So the electromagnets that we're talking about are very modestly sized, and the amount of current and power needed to create the magnetic field is very small.
Thank you, Professor.
So I guess there are no more questions. So
Like, I would
thanks
like
a
to
lot,
ask one
Professor.
question. Like,
Acha, all right. Also, guys, there's the attendance form in the chat, so you can just fill it up. Pranav, go ahead.
yeah. So, like, can we control electric propulsion in space? Like, we don't really want to give thrust all the time. So, can we control it at
Yeah,
specific time?
absolutely. So it would be very unusual if the electric propulsion wasn't specifically controlled by the ground in a very like specific and well orchestrated way. So typically the turning on and off of the thruster, the regulation of the magnetic and electric fields, the amount of propellant that we're sending through the thruster, all of the properties of the electric thruster are controlled very closely from the ground, right? So specific signals are sent so that the thrusters, we know when they're turning on, when they're turning off, how much impulse they're applying to the platform, so that we have a very clear understanding of how they would be impacting the orbit of the satellite, right? So yes, they are extremely precisely controlled from the ground at all times.
Thank you, sir. So, Lara, you can go ahead.
Lara, can you unmute?
Yeah. Can you send us your research, please? This research, or can we find it on the internet?
Yeah, you can find it. If you just type into Google my name and Imperial College, it'll bring you to my profile page. And if you go into publications, you can find the publications of my research group. So not just personally the papers I've written, but all of the research coming out of our activity. So I'd suggest reading those papers. In almost all cases, you'll be able to find access to those papers. If not, you can send me an email and I'm happy to share copies of the publications.
Yeah, kind of you, thanks.
Yeah, also if you look for Imperial Plasma Propulsion Lab, it has details on those web pages about our work in more, graphical way.
Yeah, thanks.
So there's a question by Nishan Sood. He's asking, does space debris have a high chance of causing an impact or damage to spacecraft or satellite right now?
Yes, there is definitely a high probability of space debris impacting objects. We calculate it statistically. So we say, okay, so if we have a spacecraft that has like a 1 meter surface area for every like meter squared surface area that's exposed, what is the chances of an impact within a time frame of like a year? And you can calculate statistically what that is. For an object like the International Space Station, it's hit by many pieces of debris regularly. The location at which it's hit and the amount of damage it does is, of course, random, but statistically, you could calculate that it's happening basically all the time. There's instances where astronauts themselves have been subject to like space debris impacts. Fortunately, nothing like major or catastrophic, but people are forecasting that much larger sort of disaster scenarios are going to become more and more likely as the amount of space debris increases. And I myself am aware of some like in-orbit collisions that have taken out operational satellites before. So it does happen.
Okay, so I guess now no one is there to ask questions. I think all questions have been answered. So just before summing up this whole lecture or this meeting, so I want to inform you that we have about during this meeting, after this meeting, we got around 18 new responses, 18 new applications to like submit for that. So thank you, Mr. Knoll, for having this great lecture and all. So now I guess Samriti would be summing this all up.
Lara raised her hand.
Acha, all right. No, I think that's raised from previous. I mean, that's Lara. Do you have a question?
Yeah.
Yeah, just I want to ask, when will the second event?
Yeah, it'll happen the day after tomorrow.
Yeah, it will happen on 9th.
Right. All right. So
yeah.
Do you have a question? I'm sorry. I'm sorry. Yeah, go ahead.
Before a question, I would like to tell everybody to, they can join the server. Like, please share the link, Samriddhi, in the chat. And Professor Knoll, as a high school student, I'm really interested into, this whole ion propulsion thing, right? So how do I go about researching more about it or gaining experience in that field as a high school student?
Well, I think as a high school student, you're best served actually looking at the literature. So things like textbooks, journal articles, in order to get some background in the material. In terms of next step, if you wanted to turn this into a career, then I would suggest doing a university degree, either in engineering, like aerospace engineering, or in physics. So either of those routes can take you towards graduate research. Then I think most undergraduate degree programs wouldn't cover in-depth things like plasma propulsion. So then it would be a good idea to specialize that in graduate school, like a PhD. And then you would go to a research group. So for example, mine, but there's many other alternatives, and pursue a PhD in the field of electric propulsion. And then that would sort of assure, or at least create a high chance that you would end up doing this as a profession.
All right. Also, I was curious about if you have some some places for high school students in your research work.
I have to say, unfortunately, not really. So I get approached a lot by people in high school. It's not something that the department really supports. So we do outreach events where we go to high schools, we give talks, and we put on, let's say, public exhibitions and stuff to engage with high school students. But that's different than having the high school students participate within our department and research programs. By the time you get into university, even if you're not at, for instance, Imperial, then Imperial has resources for doing exchange studentships. It's through something called the Undergraduate Research Opportunities Program, Europe, where you can apply for a spot to come and be a visiting researcher in the group. So those are open to undergraduate students. And of course, if you're studying at Imperial, then there's opportunities to become involved in the research through the final year thesis projects, group design projects, and summer internships. Okay, so there'll be more opportunities as you start progressing through education.
All right. Thank you so much.
So, all right, I guess we can end the session now. So thanks a lot, Dr. Knoll. That was a really informative session. I mean, we have people giving us feedback, and they also agree that it was a wonderful session. And I mean, thanks a lot again for taking your time out and addressing a bunch of high school students that you don't really know. So that was really kind of you. And thanks a lot for this session again.
Yes, thank you very much for having me, and thank you to all the very good questions as well. Okay, so enjoy your evening, and all the best.
Same to you. All the best.
Thank you,
Thank
sir.
you.
Bye.